In this video, we consider what happens when two wave pulses overlap at the same location in space. Right? For example, if you have a wave pulse traveling left to right and another one traveling right to left on the same string, then what happens when the two pulses collide? And the result is very simple. We simply just add the displacements. And this is called the principle of superposition. So if y1 represents the displacement for one wave and y2 represents the displacement for another wave, then the total displacement is simply equal to the sum y1 plus y2. And it's a good news that this operation is a simple addition, right? Imagine you're at a concert, you hear the singer, you hear the guitar, the drums, and your friends next to you is telling you, oh man, this is awesome. You receive all of those sound waves and they just combine by a simple addition, right? So you can distinguish the singer, you can distinguish the instruments, you can distinguish your friend. Now imagine if it was a multiplication instead of an addition, then it would be a real mess. Now we are going to have a full chapter on interference, but in this video I want to review two cases. The first one is what happens when a wave pulse arrives at a fixed end. And so, for example, let's look at a wave pulse I create on this string. Right? When the wave pulse arrives to a fixed end, you can see that the pulse is reflected, but the sign of the displacement is inverted. It's very fast, so here in the slow motion, I start with a positive pulse, a positive displacement, and it is reflected as a negative pulse. And if I start with a negative pulse, it is reflected as a positive pulse. Again, the slow motion is helpful here. Negative displacement arrives to a fixed end and comes back as a positive displacement. It's kind of hard to see on this string, but let's look at it on a torsion wave. You see, I create a positive pulse, and when it comes back, it is a negative pulse. Let's do it again. With a negative pulse, then we get a reflection that is positive. Now, how is that happening? Well, let's consider a pulse on a string that is moving from left to right. Let's look at the forces on a particle of that string. The left side is trying to pull the right side upward, and in response, the right side is pulling the left side downward. And if the two forces are exactly in the opposite direction, then the particle would not accelerate. In fact, the pulse would not propagate at all. Right? But we saw in the last video that there is a small excess of vertical force that is coming from the deformation of the string, right? That is your potential energy. And this small force will move the particle upward, converting the potential energy to kinetic energy, and the pulse will propagate towards the right side. Now let's look at what happens when the pulse arrives to a fixed end. For example, just imagine that the string is attached to a wall. Now the string is trying to pull the wall upward, but in response, the wall is pulling the string downward. And this is your action-reaction principle. No matter how much the string is pulling, the wall can respond with equal strength but opposite direction. Right? So essentially, the wall is looking at the string is trying to pull the wall upward, but the wall is saying, hey, I'm heavy, I'm not moving. Right? So all of the additional vertical force that the string is pulling is transferred back to the string in the opposite direction by the wall. And so if the pulse arrives with a positive displacement, then it comes back with a negative displacement and vice versa. Note that there is a nice trick to construct the reflected wave pulse, and it involves the principle of superposition. Imagine that there is another wave inside the wall, call it an imaginary wave, that has an opposite displacement but travels in the opposite direction. So we now have two waves, so the resulting displacement can be obtained simply using the principle of superposition. So the first wave in black here moves to the right, and the imaginary wave in red color moves to the left. And the sum of the two will be drawn in blue. When they overlap exactly, then the two wave pairs cancel each other, and the result is just a straight line. Eventually, the black pulse arrives in the imaginary space, so that means inside the wall, so we don't see it. And the imaginary pulse arrives on the left side of the wall, so we start to see it. And when we do the addition, the resulting pulse is in blue here will start to emerge as a negative displacement. But if you look at the sum of the displacement at the level of the wall, then they cancel each other, so the point on the wall is a fixed point. At a later time, the black pulse has completely disappeared behind the wall, and the imaginary red pulse is now in the real world, right? And so you can use this trick to construct a reflection of a wave pulse on a fixed end. Now, let's look at what happens for an open end. Again, looking at the torsion demo, you can see that for an open end, the reflected wave is in the same direction as the incident wave. If the incident pulse has a positive displacement, the reflective pulse is positive. Here I do it again. Positive displacement, open end, comes back as a positive displacement. And if the incident pulse is negative, then the reflected pulse is also negative. And you can see that the amplitude of the displacement at the open end is larger than the amplitude of the pulse itself. And this is because for an open end, there is no reaction exerted from the right part to the left part, right? There is nothing on the right. So the upward force is larger. And we can use the same trick, a similar trick, to find the reflected pulse. This time, for an open end, you imagine that you have an imaginary pulse that has the same displacement, but an opposite direction of propagation. Eventually, the two pulses, black and red, will overlap in space, and the result is again obtained by using the principle of superposition. So simply add the two displacements, and you obtain the blue pulse. You can see that the amplitude will in fact be twice larger than the two maxima. This is because the two maxima coincide at the position of the open end. And later, the reflected pulse is simply having the same amplitude of displacement, except that it propagates in the opposite direction. So remember this. For a fixed end, the reflected pulse is inverted. The fixed end can be obtained by two pulses that cancel each other. And using the principle of superposition, we add the displacement from the two pulses, and we obtain that the fixed end does not move. Later, we will call this destructive interference. And for an open end, the reflected pulse is not inverted. The open end can be obtained by two equal pulses, and using the principle of superposition, you find that the displacement for an open end has twice the amplitude of the incident pulse. And later we will call this constructive interference. Now, this was for a pulse. What happens if instead of a pulse, we have sinusoidal waves? Last time we learned that a sinusoidal wave traveling in the plus x direction can be represented mathematically by a wave function of the form y1 is equal to a cosine kx minus omega t, where y1 represents the displacement, a is the amplitude, k is the wave number, and omega is the angular frequency. Now remember that this is not the only possibility. Depending on initial conditions or initial position, you could have a sine function, or you could have an additional phase shift phi, so that it would be cosine kx minus omega t plus phi. And in fact, in the LibreText, we use a more general wave function, but here I'm going to use this simple wave function. Now let's look at the reflected wave. It will be traveling in the minus x direction, so it will have cosine kx plus omega t. And for a fixed end, it will be inverted. So there will be minus A instead of plus A for the amplitude. Now we have the incident wave and the reflected wave that overlap in space. And so to calculate the resulting displacement, we will use the principle of superposition. Again, the principle of superposition is a simple addition. So we just get A cosine kx minus omega t minus cosine kx plus omega t. Now we could stop here and plot this function, but there is a way to simplify this. We're going to use a trigonometric formula. So let me introduce you to my trigo slide. This will have all of the trigonometric formula that you will ever need in this course. So let's see which one we can use. We have cosine kx minus omega t minus cosine kx plus omega t. Hey, this looks like this one, right? So the two cosines will give me 2 sine kx sine omega t. All right, so we can simply simplify this, and the displacement y becomes 2a sine kx sine omega t. Now, we can look at this function on a graph. So we have an incident wave traveling in the plus x direction and a reflected wave traveling in the minus x direction. And the result is shown at the bottom. This is the black curve here. And this is called a standing wave. You see that it does not seem like it's traveling in the plus x direction. It does not seem like it's traveling in the minus x direction. So it's just standing there. If you look at the standing wave equation at the fixed position, so x is fixed to a value, say x0, then you see a function of time that is simply sine omega t, right? So it describes a simple harmonic motion, right? This is similar to a traveling wave, but all the points of the string are now in phase with each other. So all the points will reach their maximum or minimum at the same time. And all the points will go through a zero displacement at the same time also. And the fact that all the points are oscillating in phase is different from the case of a traveling wave, and we call this a standing wave. Now you can see that there are points on the string that never move, right? The location of these points are called nodes. And looking at the function for a standing wave, you can see that this will happen when sine kx is equal to 0. For the x positions where sine kx is equal to 0, then the displacement will be 0 at any time. And this will happen when kx equals 0, pi, 2 pi, 3 pi, or when it is equal to minus pi, minus 2 pi, and so on. So I will simply write this as 0 modulo pi. Now remember that the wave number k is defined as 2 pi over lambda, where lambda is the wavelength. So the equation kx equals 0 modulo pi becomes x equal 0 modulo lambda over 2. So the locations of the nodes are separated by half a wavelength. At the nodes, the string does not move. This corresponds to the two waves cancelling each other, and the incident and the incident and the reflected wave cancel each other, and we call this destructive interference. We can also look at the position where the amplitude of oscillation is the largest, right? The locations where it's the largest are called antinodes. And there will be an antinode each time the sine function is maximum. So sine kx is equal to plus or minus 1. For the x positions where sine kx is equal to plus or minus 1, then the amplitude of the displacement will be 2a. And this will happen when kx equal pi over 2, or 3 pi over 2, 5 pi over 2, or when kx equal minus pi over 2, minus 3 pi over 2, and so on. And so again, I will just write this as pi over 2 modulo pi. And again, because k is 2 pi over lambda, the equation becomes x equal lambda over 4 modulo lambda over 2. So the locations of those antinodes are also separated by half a wavelength. And at the antinodes, the amplitude of the displacement will be twice larger than the incident or the reflected waves, right? The incident wave amplitude was A, and here we have an amplitude for the standing wave of 2A. And this corresponds to the case where the two waves are adding to each other, and we call this constructive interference. All right, so that's it for standing waves. In the next video, I will consider the case when we have two fixed ends on both sides, and we will look at standing waves on a string.